Welcome to Transform Now, the podcast brought to you by robotic process automation pioneer SS&C Blue Prism. Digital transformation has the potential to reshape the way companies service their customers, engage their employees, and manage their operations. Whether you're looking to develop strategies, tactics, or best practices to positively impact the future of work, or you're curious to see how other companies have successfully navigated their digital transformation programs, then this podcast is for you. We're here to help you transform now.
Hello, everyone. I'm Brad Hairston with SS&C Blue Prism. Welcome to the Transform Now podcast. Today, I'm excited to have as my guest, Nicholas Lee, Vice Head of Solution Innovation and Consulting at Fujitsu. Nicholas and I will be talking about the fascinating topic of quantum computing and how it will impact numerous areas, including intelligent automation. Nicholas, welcome to the podcast. Why don't you tell our listeners more about yourself?
Yeah, thanks, Brad. So again, my name is Nicholas Lee. I've been at Fujitsu a little over 15 years. Predominantly, my focus is on the emerging tech domain. So I had the privilege of serving as Vice Head of Solution Innovation and Consulting. And ultimately, what that means is I work with some of our largest, global customers at some of the most complex problems that they're trying to solve. And I use my background in terms of AI and quantum and Fujitsu's kind of rich expertise in terms of IP to essentially build out applications that can solve those types of problems.
Excellent. Nicholas and I just recently met, but we discovered that we went to the same high school and the same college, although a few years apart, I might add. So we won't talk about how many. Well, Nicholas, thanks for joining. Let me ask, how did someone like you with a bachelor's degree in architecture get into the space you're in now, the world of AI, ML, quantum computing, blockchain? I mean, a lot of very sophisticated areas. How did that happen exactly?
The short answer is when I got out of college, it was very difficult to get a job, and especially in architecture. I mean, no one was really paying at that time in terms of being an architect or doing anything in terms of design. And actually I stumbled upon, it's one of those opportunities where you stumble upon someone that knows someone and ended up getting hired into essentially a technology as a telecom company. But really what I've realized over the years is that creativity is essentially essential for technology. And especially when it comes to delivering kind of that innovation edge. And so for me, I've gravitated as I've gotten into these different technology roles. And I've had, I think, 8 or 9 different roles at Fujitsu over the last 15 years. And before that, I was at Alcatel and Lucid working on some emerging technology. But what I find is that as I gravitated into those technical roles, I found myself wanting to work at kind of that innovation domain. And, now today, my background was really founded in design. And today we see design thinking really being a leading element in terms of enabling, new innovation. So it's kind of come full circle for me. But it just happened, I had a luck of an opportunity, and from there just continued to drive with, without trying to be complacent in my current role.
Yeah, I could not agree with you more that creativity is essential for technology. There's quite a few of us right-brain people moseying around in the technology world. So
Yeah,
really good point. So let's dive into the very interesting topic of quantum computing. Almost everyone has heard the term, but very few, including myself, really understand it. So can you start by just explaining what it is and get us all grounded appropriately?
Yeah. I mean, a good way, this kind of goes back to things we might have learned in college, right? Quantum information science. And that can be viewed as a synthesis of 3 of the great themes of the 20th century. So quantum physics, computer science, and information theory. So quantum technology essentially exploits the quantum effects. And this could be thought of as applied quantum information science. One could really define like a quantum computer as a machine, and that machine essentially stores and processes information according to what we call principles of quantum mechanics. And then once it stores that information and processes it, then it encodes that information into what we call qubits. So these are qubits is short for quantum, and that stores the information and in terms of superposition which of classical data with positive and negative amplitude. So that's where we start getting really into the complexity of trying to understand what that superposition means. But essentially, you're putting data into different states and that you can react onto it. And then that holds the potential to let us solve, certain problems much faster. There's things like parallelism. So you can solve things in parallel, and that's what leads to kind of speed up. Or and you do that by certain bits can be in certain positions at any time. And so you're essentially solving for multiple problems at the same time. So that's my short answer of what quantum computing essentially is.
I can see how solving multiple problems concurrently and at great speed would be a pretty powerful capability. So that's really interesting. So what's a quick, simple example of quantum computing at work that can help us wrap our brain around this a bit more?
Yeah, maybe I'll give an example of a simple answer. So quantum computing can solve very complex optimization problems. So if you're familiar with optimization, then 9 times out of 10, you probably know what a quantum computer types of problems a quantum computer can solve. The example that we use is, if you have a backpack and you can only include 40 items in that backpack, and each of those items has some sort of intrinsic value to it. Each of those items has a different weight and a different size. And so you want to pack that backpack, and you can't take, all 100 items that you might have. You can only take 40. And some of those items have value. You pack some different types of food, and you pack a plate. There's certain value that goes to those kinds of items together. And so when you start thinking about 100 items into a backpack of 40, basically the possibilities are as many stars are essentially in the galaxy. So it's impossible to try and solve that. In terms of a simple industry type of example, drug discovery is a good one, especially with everything that happened with COVID. We were looking to find new therapeutics. So these are different types of drugs that you can take that, it wasn't a vaccine, it was a therapeutic you take afterwards to mitigate some of the conditions. So these libraries, like what you want to do with the drug discovery is have, billions and trillions of options, these different elements that essentially will form stable molecular compounds. And so what quantum computing can do in that space is it can solve it very fast. And so it doesn't solve the entire problem, but takes something that would take maybe 6 months to search that billion or trillion kind of molecular library and form stable compounds that you take into in silico or in vivo testing. But it does that within minutes. And so it speeds up that whole drug discovery process. And I think the key thing is quantum computers aren't a silver bullet. There's certain parts of certain problems that they can really accelerate or really drive new differentiation. So it's essentially understanding where the quantum computer can best service a specific business application.
Interesting. When did quantum computing come onto the scene, and can you speak to the current state of its maturity?
Yeah, quantum mechanics is I think where we fundamentally would start, and that's the basic. If you think about the mathematical framework that essentially underpins everything that we're doing in terms of quantum computing, that started in the 1920s. So this has been around in terms of theories and things for a long time. Quantum computing began ultimately in the 1980s, I would say. And that was when we were proposing a quantum mechanical model. And there was a machine that we called the Turing machine, so that we refer to it as the Turing machine. And that is, I guess, the beginning of really quantum computers. And you've had these highs and lows, and you've seen it with other domains like AI and machine learning, that there's these different winters that come along and where people get excited and then it fades out. But we're now at a point where we're seeing significant investment, both venture capital, government entities, that are making companies that are making significant investment into quantum computers. We're seeing significant advancements in terms of the technology itself. And it's not just a one size fits all. There's not just one quantum computer out there that essentially is going to be the thing that ends up making a breakthrough. There's cyclical steps along the way of this journey that we're making as we continue to look for how to deliver value in terms of society or businesses.
Are there certain countries or maybe even industries that are a little further ahead in this space than others?
For sure. I mean, there was a new announcement that just came out, I think, by the White House maybe a month ago or maybe 3 weeks ago. So talking about doubling down investment in terms of quantum computing. I mean, quantum computing has the ability to, work around security encryption. Those are the fears of trying to get ahead of this technology. But there's other advantages in terms of just efficiency and productivity and coming up with new product designs. So there's so much value in this domain. The United States, I would say, is one of the bigger adopters of quantum technology. Same with Canada. So US, Canada are predominantly one of the main adopters, and then China. And then if we look at really like the main investors, so there's the adoption and then there's the investing. And if we look at the investing in quantum computing, I think China has recently invested around $10 billion, followed by Germany at 2.4 billion, Canada at 2.2, and the United States is at 1.2. So the United States is behind in terms of investment, but then you also have a lot of private owned companies, startups that are making considerable investments. So there's the government investment, and then there's the overall ecosystem. And so I would say that we see countries like China that have increased their R&D investment by more than 7% in quantum computing in a year. And then we see other countries like India and Japan. These are two significant countries that are starting to heavily invest in looking at creating partnerships or ecosystems around quantum computing. So definitely a space to watch. There's a lot of money that's going into quantum right now. And there's a lot of countries that are bidding this up in terms of ultimately seeing who's going to be the first to succeed.
So, Nicholas, you work for a Japanese-owned company, Fujitsu. Let me ask you to just speak to the role Fujitsu is playing in this space. Are you guys bringing both the hardware and the technology side as well as the consulting to complement that?
Yeah, good question. There's actually, I call it the three-pronged approach. So we have what's called quantum inspired. So it's, we call it the digital annealer. It uses similar quantum algorithms that you'll run on future quantum computers, but you're not dealing with, the qubits. And with the qubits, you need like supercooling, superconducting, super costly types of environments. So digital annealer is a good stepping stone for companies that want to invest in quantum computing, but want to deliver something that's going to deliver value for the business. It's hard for, executives to go in and say, hey, I'd like to invest in quantum computing when it's 4 to 5 years away and make that case to the board, or be able to solve a problem, but it's only a toy problem in a lab. So that's Fujitsu's first step, is the quantum inspired domain. We just announced that we launched the Fujitsu's quantum simulator. We have one of the largest qubit simulators in the world right now, 36 qubits. Quantum simulation is more about finding algorithms in the future that are going to be stable. Because when you use a real quantum computer, by the time you look back to see what happened to get that result, it is essentially destroys, you can't find out what's happening inside the quantum computer. So quantum simulation serves as a purpose for helping us to understand quantum algorithms and essentially build better quantum systems in the future. And then we're also building a superconducting quantum computer with Riken and University of Tokyo. And so we're focused on both long-term quantum gate. We're focused on quantum simulation to improve the process and algorithms. And then we're focused on something that can deliver real value today. And at those layers, we're at the software layer, we're at the hardware layer, we're at the full stack, plus the consulting technical professional services on top of that. So I would say we're all in on quantum computing.
Sure sounds like it. So you talked about a few examples, use cases. I'd like to maybe delve into that a little bit more. Could you talk about some other common use cases that quantum computing is kind of got its sights set on? I think that would be really interesting to hear some more examples.
Yeah, I mean, the one I mentioned before, drug discovery, is obviously there's a lot of money in pharma. A lot of people are interested in how this can help. AI and machine learning is already utilized there today. It's not a hard lift to move to a better compute, platform. Traffic optimization. These are problems that you have a city like the size of Tokyo, and you're trying to optimize, vehicles through that process and the traffic lights and all that. It's a super complex problem, and it changes. And so the advantages of quantum computing in that aspect is the speed up. So you can constantly do that optimization of the very complex problems, and then completeness. So you can take into account more variables as part of that traffic optimization. I'd say drug discovery, traffic optimization, we're seeing a lot in terms of new material science, which is very similar to the drug discovery process. A lot of people historically If you look on social media, they're talking about portfolio optimization, financial services. Can we trade stocks better and do that using quantum computers? There's an approach of arbitrage and essentially how we tackle those types of problems. So a lot of focus on financial services, cybersecurity, quantum key encryption. But
Right.
I think that, for me, the biggest areas I think of potential material science, drug discovery, and then there's other things in terms of retail sectors or public sectors that are super interesting. I think will be quite transformative.
Yeah. I think if we could go back a couple of years and think about what it would have been like to get the vaccine maybe 6 months, 9 months earlier
Yeah.
by virtue of using quantum computing, I think we'd all go for that.
Yep.
That would have made a huge difference.
During the whole vaccine and the pandemic, we worked with the US Army. And one of the things we did was vaccine distribution and PPE allocation distribution. How do you get vaccines and PPE materials out to the right groups at the right time? So we had the frontline workers that needed it. We had different states that needed different distributions. We have different locations within states. And so that's a super complex problem that used the digital annealer, the quantum inspired computing to essentially solve that. So just wanted to add that on.
Yeah. Oh, that's great. What about climate change? It's such a huge topic right now. Could quantum computing play a role in mitigating climate change, do you think?
Yeah, absolutely. And I just authored actually a thesis on quantum tech for climate mitigation. And so,
Okay.
I mean, there's over 80 something use cases that we've identified for climate, the intersection of quantum and climate. And,
Yeah.
if you look at climate, we're adding approximately, I think it's 51 billion tons of greenhouse gas to the atmosphere every year.
Mhm.
And we're trapping heat, driving up global temperatures. And we haven't been successful, right, in terms of mitigating this. I think we want to be successful, we need to be getting to a net zero position. And that's challenging. So I think we see quantum computing. If you look at investments in terms of climate mitigation, quantum computing could be that disruptor. It's all about optimization, reducing the time that cars are on the road. We have a solution that we're pioneering in that space, right? So 25% kind of reduction in terms of your emissions outputs. But we look at essentially the quantum and climate intersection in three aspects. One is, technology feasibility, like could we do this? And maturity, like how well can we do it? And then we
Right.
look at, the abatement potential, how impactful would these use cases be for the ultimate climate? And then adoption and scale, like is this something that is going to work in society? Are people actually going to consume it? And so to avoid a climate disaster, this is our greatest, I think, challenge of the century. And to make it happen, I think we need to transform everything that we're doing. And this ultimately means that we need to find breakthroughs in terms of innovation. And I think that's where quantum computing can help.
Okay. So how could quantum computing impact the world of RPA and AI?
When we solve a production problem using like the digital annealer or quantum inspired computing, we already use AI in that. So AI is done for pre-processing, data transformation. We use the digital annealer for specific combinatorial aspects of the problem. And then we also use, classical solvers or high performance computing. So when we think about the world of quantum computers, I call it hybrid algorithms. That's essentially how we're going to solve and add value. So for AI, I think AI is already part of the equation, and I don't see too much of a change in that. I think for RPA, in terms of benefiting from quantum computing, I think there's some changes in terms of, and I can talk specifically about what those changes might look like. But I think RPA and AI, they're here to stay. It's complementary to quantum computers. It's about enabling that quantum computing, whether it's, we optimize something and then we need to action that off, or it's actioning
Right.
something to get to that quantum process.
Yeah. You look at the way RPA has evolved and now it's taking advantage of AI. It's getting insights that it can, as you said, can act upon. If it can get those insights 100, a million times faster, it's going to drive faster response, faster action. So to me, everything you're saying makes perfect sense. It looks like it could, have a huge impact in enabling RPA digital workers to get those insights more quickly and then act on them in a way that's going to benefit an organization. So let's talk about what are the top constraints around quantum computing? I assume quantum computers are not cheap. So there's probably a financial constraint, maybe hardware, but also talent, people like you that understand it, that can wrap their brain around it, bring it to bear in a very complex problem. So could you just talk about that, some of the constraints that need to be addressed in moving in this direction?
Yeah, I would say all of the above, but I think it really depends on your starting position. The hardware players today, my view is they're less oriented towards business utility. So when you talk about true quantum gate-based systems, they're still in a lab, they're solving smaller problems, they're interested in the use cases, but they're getting tons of money from venture capitalists or government entities. And so they're less oriented about the business aspect of that. They are interested in progressing how many qubits and the fidelity of the qubit, things like that. Organizations, on the other hand, they're searching for use cases, like where can I find value? They want to develop a quantum computing strategy. And so that will help them substantiate opportunities and investments internally, grow their own internal talent. So there's two different paradigms in terms of what both of those organizations are looking at, or both of those kinds of entities are looking at. And then you have talent in general, and it's been very fragmented, I would say. You have the business folks that, are talking a lot of hype about quantum and looking at where we can apply the quantum business. You have the technical minds that are looking, the architecture and how do we design better solutions. And then you have like academia, and you see have a number of different players in there. It's quite fragmented. One of the things I tried to do back in 2020 was I started a LinkedIn group called Entangle. And essentially the whole purpose of that was to be an open group and try and bridge the divide, to bring the conversations together. Same thing we're doing with, quantum and climate. You have really focused people on quantum, really focused people on climate, very few people focused on the intersection of quantum and climate. So, my focus outside of Fujitsu is to build an ecosystem to bring those kinds of conversations together. And so that's what I've done with both Entangle and the quantum thesis. But for me, it's the constraints are everywhere, right? It's a difficult space to be, because this is super complex, never been done before, very disruptive, but it's also super rewarding because you're working on some of the most interesting problems in the world.
Yeah, no doubt. Nicholas, let's wrap up today by just getting some of your predictions for quantum computing. First off, when do you think it will be mainstream for most companies? Could you speak to that and then add any other predictions or thoughts you have?
Yeah, I mean, it's hard to pinpoint. There's been a lot of conversations. I hear 4 or 5 years, what we're saying for quantum gate. But for me, the way I answer it is it's not a light switch, right? It's not going to be like one day we're going to wake up and everyone's going to have quantum, computers. Organizations, I'd say institutions and really governments understand this. And the whole thing about it's not really a silver bullet. Quantum computing doesn't solve the entire problem in itself. It's about hybrid algorithms. And so I look at quantum as just another tool in the toolbox, right? And there's multiple flavors of quantum. There's the annealers, there's simulators, there's emulators, and there's gate-based. And so each of them has kind of a different relevance point of when it's going to add business value. Annealers today we're scaling up to 100,000 with 1 million variables in lab. So this is production business value today. It doesn't use a real qubit-based system, at least ours doesn't. But this is where you can really solve something with a quantum algorithm and deliver business value. Simulators I mentioned are really, if you want to find the next algorithm and tune it and get it ready for the next 4 or 5 years, it's not going to deliver immediate, I would say, business value today, but it's that longer term investment. And then gate-based computers, very much lab focused. 4 to 5 years from now, there'll be some utility there. So there's different starting points. There's not going to be a single kind of, aha moment of now we all have, quantum computers. And it just depends on your organization's the propensity to want to invest time up front. And then, what your goal is. If you're trying to demonstrate something and deliver value today, then annealers are probably better for you. If you have long-term kind of line of sight and you just want to learn about it along the way and you want to be ready when it comes, then maybe a gate-based or maybe some hybrid of a couple of different, solutions. But, it's coming for sure. And it's just a matter of time.
Well, Nicholas, it has been a true pleasure having you on the podcast today to educate us on quantum computing. It's a fascinating topic that I really hope to learn a lot more about. And I think it's going to impact so many areas of our lives. We've talked about many just today on the podcast, but it's hard not to imagine how this is going to be a really positive lever on many different areas of technology, including intelligent automation. So thanks for being on and sharing your thoughts and your ideas and your predictions around quantum computing. Really interesting stuff. And I wish you the best.
Yeah, thanks, Brad. No, I appreciate it. Happy to collaborate.
Thanks for tuning in to Transform Now. For more insightful discussions on digital transformation and more, check out our podcast channel where you'll find all of our previous episodes. And to make sure you never miss an episode, subscribe to the show on your favorite podcast player. And if you like what you've heard, please leave us a review. For more information about digital transformation and the future of work, check out blueprism.com to learn how SS&C Blue Prism's digital workforce is enabling enterprise transformation now.